Now that we've had the opportunity to talk about the basics of what summation notation means, let's establish some common formulas, some rules and tips and tricks to make calculating those sums a little bit easier. So to begin with, let's look at this example where we're taking the sum as k goes from 1 to capital N of a function which doesn't depend on k at all, of a constant function. Now if I plug in k equals 1 to this function, the output will be c, and same for k equals 2 and k equals 3 and so on, all the way up to k equals capital N. And so I, as a result, end up adding c to itself n times over. And as a result, if I want to calculate the total value, I can just take that constant of c, multiply it by the number capital N given to me on the top of the sigma, and that will be the result of this sum. We also have a special formula in the case that the function that we're summing over is just equal to k itself. So in this case we have 1 plus 2 plus 3 plus 4 plus ... all the way up to plus the final value of capital N. The shortcut for calculating this is that you can simply take capital N, multiply it by n plus 1, and divide that product by 2. And the reasoning for this is very cute, and I will add a video to show why this formula holds true. Finally, we'll also commonly encounter the sum as k goes from 1 to capital N of k squared. So in this case, we'd have 1 squared, 2 squared, 3 squared, 4 squared, all the way up to the top value of capital N. And this can be found, again, by taking a fraction, where in the numerator we have n times n plus 1 times 2n plus 1, all over 6. Now, I don't necessarily expect you to memorize these formulas, but you should have them in your notes in a pretty handy place so you can access them easily as you're doing the homework and the problem sets. Now let's try and apply them down here with some exercises below. Let's start by calculating the value as k goes from 4 to 300 of k squared. And actually, there's a little typo here. I should read 1 for the moment. K equals 4 is the next example. Okay, now this is almost an exact replica of the sum as k goes from 1 to capital N of k squared, except for the single modification that capital N has been replaced by 300. So I'll just make a note of that down here below. Capital N equals 300. Now I can make that same modification in the formula on the far right hand side to say that this sum is equal to 300 times 300 plus 1 times 300 times 2 plus 1 all over 6. And this large number, whatever it happens to be, would be the value of this sum. Now let's consider a similar example. This time, what is supposed to be the sum as k goes from 4 to 300 of k squared. Now, in this case, we are unable to apply the above formula directly, because the above formula is valid for a starting value of 1, and we have a starting value of 4. We have the sum as starting from 4, 4 squared, 5 squared, 6 squared, up to 300 squared. And the formula that we have, this formula here, this is saying what we would get if we started the sum at 1 instead of at 4. But notice something. This sum, starting at k equals 1, can be adjusted to start at k equals 4 by just subtracting off the 3 extra values that appear in the front. If I subtract off 1 squared, and I subtract off 2 squared, and I subtract off 3 squared, then I'll cancel out the k equals 1, 2, and 3 k's, and I'll be left just with the 4 and beyond that I am looking for in this summation. So if you simplify this number, you'll have the result of this summation, which starts at 4 instead of at 1. Now you can also run across a situation where you're trying to take the sum, but the function over which you're summing, the f of k, is slightly more complicated. And so we can use this basic principle that if you're taking the sum from some starting value to some final value, and let's say that you're taking the sum of a sum of difference or two functions, then you can split it apart, take the first sum, take the second sum separately, and add these two results. As well, just like we have for derivatives and integrals, we have a constant multiple rule for sums, which says that if you're taking the sum of some number, some constant, times a function, then you can ignore that constant till the very end of the problem, sum just the function, multiply by the constant later. So let's see what benefits these rules have for calculating something like this. Find the value of the sum, k goes from 1 to 100, of the quantity 3k plus 5. What's beautiful about the rules that we have just listed is that they enable us to pull out 3, take the sum from 1 to 100 of just the function k, and then separately take the sum of the second function, just 5. Now we have this formula for what to do with the sum as k goes from 1 to 100 of k. We can take that capital N, multiply it by capital N plus 1, and divide the result by 2. We also had a formula for what to do when we had the sum of a constant function, as we do here in the back. Take the constant 5 and multiply that by the capital N that we have. And this number, when it's simplified, will be the value of the sum that we were asked to find. So using these rules in combination with these three common summation formulas will help you to quickly calculate the value of most of the sums that you'll encounter in this class.